All right, the development of the quantum mechanical model part 2. So continuing on from Einstein and his photoelectric effect. Learning targets. Now we're going to describe the scientific discoveries that led to the development of the quantum mechanical model in terms of de Broglie and the electron wave particle duality. First one to propose that the electrons also had this wave particle duality or particle wave duality. Heisenberg and his uncertainty principle, and Schrödinger and the wave functions and wave equation, which is going to lead us to be able to define what an orbital is. So we need to be able to define that at the end of today. Now, de Broglie, he's given credit for defining the fact that electrons also can behave like waves and behave like particles. So whereas light may have been thought of as being a pure energy and wave, and then they added on the particle part later, electrons were always thought of as just being particles. But the idea that they could move in a fashion similar to waves, like the light could, and move in that fashion like light could, is where de Broglie comes in. Now, that they actually do exhibit properties of waves. The electron is only allowed certain possible wavelengths, since an electron has a wave-like motion. And basically, he came up with his own equation, but we don't really need to know his equation. But he pretty much said anything that is a particle, even like a person, is going to have wave-like characteristics. We're going to give off of course, we're a big, huge mass, so we give off very small, tiny, little, minuscule wavelengths. But things that are really small, like electrons, of course, they have, wavelengths that would be a lot larger than, say, us that have a whole lot more mass. But his experiments and looking at diffraction patterns and all of these investigations that he looked at, he proposed this particular part of the theory. And what do we mean by diffraction patterns? Okay, so the idea of creating waves. This one's more of like using water, but you can see the waves and how they have interference. Okay, they end up hitting each other and canceling each other out and having interference. Well, they decided to do that with the electron here. So what we can do here, so they shot electrons through the slits here and got a similar diffraction pattern as seen with regular light, which was kind of impressive. So here, the resulting interference patterns, as you can see, here's visible light on the left. The electrons are on the right. They have a very similar pattern. Yeah, there's definitely some notable distinctions that are different, like the white patterns on the electrons are definitely thinner in certain areas. However, but it does establish a very similar idea of how the electrons are moving in terms of a wave-like fashion. Now, the wave-particle duality idea, of course, Heisenberg, all of these people, start looking at these different concepts and start molding their own thoughts about it. Wave-particle duality is kind of thought as a complementary property. If we know more about one of them, then we know less about the other. So if we know more about the wave-like property, we know less about the particle property, and so forth. And this is kind of where Heisenberg came in. The velocity of an electron is more related to its wave-like nature, and the position of the electron is more related to its particle, because you can hit it and that it has mass and it's behaving more like a particle. So basically, based off of this idea that they are kind of like contrasting properties here, where if we want to know more about its velocity, we know less about its position. If we want to know more about its position, now we're going to know less about its velocity, and those things aren't going to be able to be known all at one time. So the uncertainty principle is what he developed. And the uncertainty principle is fundamentally impossible to know the position and the velocity of an electron at the same time. And let's look at this diagram and kind of absorb that particular idea. So here we have an electron, and we're going to hit it with some light, some photon, to figure out where it is. But remember, the photons and electrons are pretty small particles. So once you hit the electron, it now has a new path and new velocity. So you kind of don't know where it is anymore, and you don't know how fast it's going. So the idea of being able to know its position and velocity at the same time as another building block towards this quantum model, because the quantum model is actually a big statistical probability model. So this idea that we don't really know exactly, but we can plot it, we can do electron densities, but we're not going to actually know where the electrons are after you plot that particular point, because now it's moved and now it's going in a different direction and it has a new velocity. But this led to the idea that it's kind of indeterminate. So when we're predicting where electrons are in the cloud, in the electron cloud, it's really a probability idea. And Schrodinger, of course, comes along here and he does his wave function, and he creates this wave equation showing these 3D graphs of certain shapes. And these 3D graphs are the quantized energy levels. They're actual three-dimensional spaces with different shapes. And this is where we're going to have the probability of finding an electron. So he developed a formula to treat the electron as a wave. And some people call them wave functions, or they call it the wave equation, but it's really wave functions because each one has its own, way of calculating it. And this one is the wave function for the 1s orbital. So this is only one particular of the wave functions or wave equation. And yes, it has a Greek letter and it's all this weird calculating stuff. We would never ask you to calculate these things, but do understand that, and this is way beyond my math ability as well, of trying to figure that out, that they can be solved mathematically. They can put all the numbers in and then pops out, here you go, here's your graph. And you can see what it looks like. What is the three-dimensional shape? So that brings us to the quantum mechanics of it. These 3D graphs that have different shapes and energies are known as orbitals. And here we show you the s orbital. The s orbital is probably the easiest, most simplistic one because it's spherical in shape. It's just like a round ball. But what are these different orbitals? They are a region in space where 90% of the time, it's a 90% probability we are likely to find the electron, and that place is the orbital. Now, the spherical shaped one is only one of the possible orbitals the electrons can fill or be in. Here is a picture of many of the orbitals. The S-shaped one here, spherical. The p orbitals are dumbbell, and there's 3 of them. There's one on the x plane, one on the y plane, and one on the z plane if we're looking at a graph, okay? And these ones are called dumbbell shapes because they kind of look like dumbbells or whatever. I don't know. That's what they call them. Now the D's, which are the ones here in blue, there are 5 of them, and they look kind of like funny balloon animals if you ask me. And then this one in the middle has this like donut thing in the middle. Definitely weird shape there. And then the F's are even more complex, more funny balloon animal type looking things. And then we have the one with the double donut in the center. Now, of course, by no means are you expected to draw these or really even remember much more than the fact that S has a spherical shape and P we call the dumbbell shape. Let's summarize this. Wave functions only give the probability of finding the electron. Once again, probability 90% of the time. Electrons do not travel around the nucleus in neat little orbits like Bohr suggested. Instead, they exist in 3-dimensional regions of space around the nucleus, which are known as orbitals. So those 3-dimensional spaces that I just showed you on the previous slide, those are going to be where these electrons are going to be assigned. And I'm going to show you how to assign them, the system of assigning them on Thursday, next class. We're going to look at how to do that. So one more little tidbit here, as you can see, these are electron density graphs. You can see the D looks like a double dumbbell, so it's kind of not as round as those other ones, although they're drawn that way. The dumbbell shape here, the spherical shaped one of the S, and so forth. Foundation of the theory was laid by Schrodinger's equation and Heisenberg's uncertainty principle. Of course, all the other ones, the photoelectric effect, Planck, and all of them built up to that point, adding more insight and more observations as to how light behaves, so they could translate that into how electrons behaved. Now, electrons, this is the ultimate summary statement right here. Electrons behave as waves and particles, and they can be described mathematically with those complex wave functions equations. So you can, take that what you will, but they are being described mathematically, giving us this 90% probability of where they are likely to be found. Now, at any point, you can go back and watch the video link here. This is the one that's in the Edpuzzle, where you don't have the questions to stop you along the way, but it is a really good video, and he draws the orbitals, and it's very nice, thorough assessment of the progression of the quantum mechanical model over time. So if you need to go back and rewatch it, the link is right here in the PowerPoint. Last but not least, this is how we're going to translate it into filling the orbitals, filling them in their correct configuration, placing the electrons around the nucleus in the atom. Luckily, we don't have to really deal with all the shapes and stuff, because there's going to be a system from the periodic table that allows us to place them in order of how many electrons they have. And it's going to be following this block system. The first two columns, the alkali metals and alkaline earth metals, along with helium over here, they are considered the S block elements. So you're going to have S orbitals, or you're going to be ending on S orbitals for those configurations. The green ones over here, everything but helium in the other tall columns, those are considered the P block elements. So the P orbitals, that's where they'll end. And then here in the yellow is the transition metals. They are the D block elements, and they end pretty much on D orbitals. And then the F ones down here, the lanthanides and actinides, the inner transitions, those ones end on the F orbitals. So we'll be looking at using the periodic table to help us assign them when we go into electron configurations and orbital diagrams next class.